So my talk today is about a non-hydrostatic Isopycnal-Coordinate ocean model. The abstract for this talk is as follows. Numerical models of small-scale processes such as internal waves require computationally expensive non-hydrostatic simulations and high horizontal grid resolution. The horizontal grid resolution that you need to resolve these non-hydrostatic effects scales like some depth scale. So in the case of internal waves, the horizontal grid spacing must be less than the depth of the internal interface. Isopycnal coordinates provide a natural representation of a stratified fluid, and so they reduce the number of vertical coordinates, vertical grid layers that you need, and this improves efficiency. Existing isopycnal coordinate models are purely hydrostatic, and so I'll tell you about a little development to make it non-hydrostatic. So the ocean is sort of the multi-scale problem that we have on planet Earth. This diagram shows a variety of ocean processes with a spatial scale and a time scale, and at the very end we have climate. This has spatial scales on the order of the circumference of Earth and time scales on the order of tens of thousands to hundreds of thousands of years. At the very small scale we have turbulent mixing, which at the smallest scale is on the order of the Kolmogorov scale, which is about 1 millimeter. And what's interesting about this problem is that throughout this range of scales you can have interactions. That is, the small scale turbulent motions can end up influencing things like climate. And a famous quote from oceanography sort of captures this, which is, without deep mixing, the ocean would turn into a stagnant pool of salty water. And one process that we're sort of interested in studying in this range of scales is internal waves, because internal waves are thought to be a primary link between the large scale processes and the rapidly evolving centimeter scale mixing. So just to give you a brief background on internal waves are disturbances that propagate in the interior of a stratified fluid, usually on an interface of density variation, or what's called a pycnocline. And this variable rho represents the density, and in this situation we have fresher and warmer water sort of sitting on saltier and heavier water. And internal waves are very important to physical and biological processes such as upwelling and nutrient transport on the continental shelves. They're also very difficult to model because we have a range of scales on the order of turbulence on the order of millimeters and meters. These waves can have wavelengths on the order of kilometers, and they can propagate across entire ocean basins on the order of thousands of kilometers. Internal waves are also computationally expensive because they require non-hydrostatic models to resolve the dispersive properties of these waves. And this usually requires a 3D pressure Poisson solve. So this is a schematic of the life cycle of internal waves. Internal waves are usually generated from tidal flow over ridges and bathymetric features. About almost 1 terawatt of tidal power is converted into internal waves, and all this power ends up being dissipated from internal wave breaking on the shelves. During the second stage of the life cycle of internal waves, these waves can propagate across entire ocean basins and steepen and form trains of solitary waves like you see here. And this is the part of the life cycle of internal waves where the non-hydrostatic effects matter, because the non-hydrostatic dispersion balances the nonlinear steepening, and this gives these waves their shape. And finally, when these waves encounter continental margins and continental shelves, they can break and dissipate their energy. So here's a few examples of some satellite images of internal waves, and it might be hard to see in the back, but you can see these trains of solitary waves, and what you're seeing is the surface expression of these internal disturbances. You're seeing sort of surface convergences and divergences in these images, and they provide very striking examples of, you can actually sort of see the manifestation of these waves. So to model various processes in the ocean, we generally can't take the Navier-Stokes equations and apply it throughout the range of scales. We have to make models that are sort of tailored to very specific processes. And in this case, you can sort of see the regimes where hydrostatic models or global ocean models or regional ocean models are valid, that is for the large scales. And these models are valid for sort of relatively low aspect ratios where you have the depth, which is h, which is much smaller than the horizontal length scales. And if we just sort of look at a schematic of the ocean, we can sort of see that this is the case. That is, the ocean has extremely large horizontal length scales on the order of thousands of kilometers, and what I'm coloring here is the depth. You can see that the average depth of the ocean is only 4 kilometers. So if you do a back of the envelope calculation, you can see that the ocean has about the same aspect ratio as a sheet of paper. That is, it's extremely thin. So in this case, we can use hydrostatic models to really capture these processes very well. However, for smaller scale processes that have flow aspect ratios where the depth is on the order of horizontal length scales, we need non-hydrostatic models. And these are sort of the processes that we use to, that we model with non-hydrostatic models. On the very small scale end, we have the typical CFD models. And the difference between CFD models and ocean models are basically that we have a free surface. The first non-hydrostatic ocean models were developed not too long ago to overcome some of the limitations associated with the hydrostatic equations. That is, the hydrostatic primitive equations are ill-posed with open boundary conditions, and also they're inaccurate for the representation of small-scale features. The difference between hydrostatic and non-hydrostatic models is shown on this slide. The major difference is the treatment of the vertical momentum equation. When the aspect ratio is small, the vertical momentum equation reduces to the hydrostatic balance. And in this case, we can calculate the pressure as just the integrated weight of fluid overhead. In non-hydrostatic models, we have to solve a pressure Poisson equation, which is very computationally expensive to capture the pressure. The nice thing about non-hydrostatic models is that pressure gives rise to dispersion, which is the variation in wave speed with wave number. Hydrostatic models, on the other hand, all of the waves travel at the same speed. Also, what's unfortunate about hydrostatic models is there's very limited depth variability. That is, the entire water column feels the effect of the free surface, whereas in non-hydrostatic models, it decays away from waves. So the major difference between hydrostatic and non-hydrostatic models is really the computational effect. We'd really love to use hydrostatic models, but they are inaccurate. And non-hydrostatic models, on the other hand, are very accurate at small scales, but they are expensive. And one of the reasons that they're so expensive that I've shown is because you require extremely high horizontal resolution to even resolve the non-hydrostatic processes. I wrote a paper on this which showed that to actually capture non-hydrostatic effects, you need the horizontal grid spacing to be less than some depth scale. And for internal waves, this is the depth of the internal interface, which is on the order of tens to hundreds of meters. And I've derived this condition by assuming that the case that you need for the numerical dispersion to actually be smaller than the physical dispersion due to non-hydrostasy. And this is the condition for second-order accurate ocean models, which is actually most of the ocean models out there. And sort of intuitively, this grid resolution requirement makes sense because non-hydrostatic effects operate for aspect ratio flows that the horizontal length scales are similar to the depth. So the relevant length scales that we need to resolve in the model scale with the depth. So just to illustrate sort of consequences of this resolution requirement, this is just a simulation of internal waves with very high resolution. And in this case, we form a nice rank-ordered train of solitary waves, which is sort of the converged solution. On the other hand, the hydrostatic model sort of forms a shock or a bore. And if you zoom in on the front of this, you see that these little wiggles, which are actually numerically induced solitary waves. At low resolution, the non-hydrostatic and the hydrostatic models produce exactly the same result. And this is because that the numerical dispersion, which is very large in both situations, is overwhelming each of these solutions. And so, because we require very high horizontal grid resolution, I'm proposing that we probably will need some means of reducing resolution requirements. And I think isopycnal coordinates are a nice way of doing this. Isopycnal coordinates just mean that the coordinate is density. So our grid lines follow lines of constant density. Compared to other coordinate systems like z coordinates, which have fixed levels in the vertical, and sigma coordinates, where the coordinates represent a percentage of the depth, we can use a much reduced number of grid points in the vertical. Isopycnal coordinates also reduce spurious diapycnal mixing because we're no longer fluxing a scalar-like density through our grid cells to keep track of it. That is, the lines of constant density move with the flow. Now, some challenges of isopycnal models include that we cannot represent unstable stratification. And also, things like layer outcropping or wetting and drying of isopycnal layers require special numerical schemes. And finally, a challenge of isopycnal models is that the existing ones are purely hydrostatic. And what's the reason behind this? What about a non-hydrostatic ocean model? Well, there's this paper that talked about this that said that common sense suggests that pure isopycnal coordinates should not be used for non-hydrostatic ocean modeling. And this is, of course, pointless, this approach of using non-hydrostatic isopycnal models, since non-hydrostatic effects are associated with overturns, such as Kelvin-Helmholtz instabilities. And this is certainly a valid concern. However, if you look at these processes in the ocean, they're an extremely small-scale process that is usually not resolved in most ocean models. And furthermore, there are a lot of non-hydrostatic effects that aren't associated with overturns, such as internal waves and the formation of solitary waves. And so I tried not to get discouraged when I read this and thought that it still might be a good thing to try to do to make a non-hydrostatic model. And so this is basically what I came up with. For this model, we're solving the incompressible Navier-Stokes equations with a free surface in an isopycnal coordinate system. It uses a second-order accurate and time and space finite difference method for the momentum and a finite volume equation to keep track of the layer heights. We use a staggered C-grid layout where the velocities are located on the cell faces, and properties like the layer heights, H, and the non-hydrostatic pressure are located at the center. We split the Montgomery potential, which is the equivalent of the pressure gradient in isopycnal models, into the barotropic, which is due to the free surface, and the baroclinic, which is due to these interfaces. The barotropic part moves a lot faster, so we discretize that part implicitly, and the internal waves explicitly because they're slower, and that's the features that we want to capture. We use these implicit-explicit multi-step methods from Duran 2012 with implicit vertical diffusion, which you essentially have to do if you have drying of layers. We also use explicit horizontal diffusion, which is sort of the standard in ocean models, and various pressure projection methods to solve the non-hydrostatic pressure. So I've tried to validate this model as best as I can with analytical solutions. And here's the schematic of some different configurations of the model with just a free surface oscillation in a tank, internal interface with a two-layer stratification and with continuous stratification. And the model does a very good job of actually capturing the dispersive properties. Furthermore, the same tests you can do with the actual velocity profiles that you get from analytical solutions and from modal analysis. And again, the model does a very nice job of capturing the dispersive properties. I've also done some tests on the formation of solitary waves compared to other non-hydrostatic models and compared to laboratory experiments. And it's nice to see that the model is actually capable of forming solitary waves that have sort of converged to the right shape. And finally, I'll just show a couple of simulations. And the difference sort of between these two simulations is sort of in the two regimes where we have very few grid points, which is just a simulation with just 2 grid points of steepening of internal solitary waves formed from oscillating flow back and forth over this ridge. You can see that this tidal flow depresses the isopycnals, and then it releases a train of solitary waves, which sort of propagates away from this. And this is just a model with just 2 layers. So it provides a very sort of nice reduced way of capturing this problem. And at the other end, we can sort of see what happens from tidal flow when we have a series of isopycnals. Again, we have tidal flow over this ridge. And when you have a continuous stratification, that is, density varies linearly from the top to the bottom. In this situation, the internal waves actually propagate away from this ridge along these characteristic lines, which are the internal wave beam lines. So it's very cool to sort of see this behavior in the continuous stratification that all the waves propagate along these beams. And it's kind of interesting to see the sort of the connection between the beams and the isopycnals. So just to conclude, non-hydrostatic models are very computationally expensive, and this is because they require the solution of a pressure Poisson equation, and it requires extremely high horizontal grid resolution to actually resolve the non-hydrostatic effects. Satisfaction of this condition is really a significant additional resolution requirement beyond the current state of ocean modeling. And I think it really demonstrates that supercomputing will definitely play a role in ocean modeling simulations in the future, especially in non-hydrostatic simulations. Finally, I've just shown a new isopycnal model that is intended to sort of reduce the number of grid points that you need to provide a better representation of the problem. And it's able to capture a variety of non-hydrostatic processes. And finally, I'll get to the real purpose of my talk, which is just to thank the Department of Energy CSGF program so much for all their support over the past several years. Thanks.